Welcome to the third lecture on Sudoku in Haskell, and we're going to be wrapping things up today by seeing how we can transform the simple Sudoku solvers that we wrote in the last couple of lectures into a highly efficient Sudoku solver that can solve any of the puzzles more or less in an instant. So as usual, we're going to start off with a quick review of what we did last day. So here are our basic declarations, because as usual we're going to be using these quite a lot today. So just a quick refresher that a Sudoku grid is a matrix of values, a matrix of things is a list of rows of things, a row is simply a list, a value is a character, and choices is simply a list of values. So make sure you're all familiar with these basic data type declarations. So what we did last couple of times is we defined a few Sudoku solvers. So I'm going to quickly review these and also kind of talk through the problems with these, and that will lead us into kind of having a very efficient Sudoku solver, which we're going to end up writing today. So the first solver we wrote was a very basic one, and it was called solve, and it took a Sudoku grid as an input, and it gave a list of all possible Sudoku grids which solve that puzzle as an output. And again, if you want to just have one Sudoku grid, then you just simply take the head of that list, and under lazy evaluation that will just compute that and nothing else. So the way this actually worked is it was defined as a simple composition of three functions. It was a nice one-line program, and what we did is we filtered the valid grids after collapsing after making choices. So let's talk briefly through what each of these three functions actually did. So what choices does is it takes your initial Sudoku grid, which are given, for example, the easy grid, which we had, and it replaces each blank cell by all possible choices that we could have for that cell, 1 to 9. And it doesn't try and do anything clever, it simply replaces each blank cell by all possible choices 1 to 9. Then what the collapse function does is it considers each of the cells, and it considers all possible combinations of all possible values in each cell. And again, I mentioned maybe this should really be called something like explode, because this actually really explodes the search space. And then finally what we did in the end is we filter out the valid grids, and valid simply means that there's no duplicates in any row, any column, or any box. So in principle, this Sudoku solver actually works, but in practice we found that it doesn't, because, for example, for the easy grid, at this point, coming out of the collapse function, there were 9 to the power 51 possible grids coming out at this point. And that's because in the easy grid, there's 51 blank cells. So when we consider all possible combinations using the collapse function, we get 9 to the power 51 possible grids coming out. So this Sudoku solver in principle works, but in practice, it will never terminate in anybody's lifetime. So we need to think a bit more. So what we did then is we thought about the idea of pruning out invalid choices. So this led us to our second Sudoku solver. So we had a Sudoku solver called solve2, and it had the same type as before. And it's defined in much the same way. So we filter the valid grids after collapsing, after pruning, and this is the new part, after applying the choices function. So this is basically the same as the first solver, except we've added one new function here in the composition. We've added the prune function. And what prune does is it removes any choices which occur as single entries in a particular row, column, or box. So for example, if you had a 1 in the top left-hand corner of your Sudoku grid, then there's no point in having a 1 anywhere else in that row or that column or that box, because you've already got a 1 in the top left-hand column. So that's what the pruning function is doing. And then what we found is that when you try that out with the easy grid, it does reduce the number of possibilities. So you get down to about 10 to the power 24 possibilities in here. possibilities. But that's still an enormous number, so it's not actually tractable to solve Sudoku puzzles using this function. So then what we did is we introduced the idea of actually just iterating the pruning function, and this led us to our third Sudoku solver, which is the final one which we did last day. And what we did here is we iterated the pruning function after applying the choices function. So the only change here is we're now computing a fixed point of the pruning function. And a fixed point of a function is an input that when you apply the function to it, you get the same result back as you were given. Okay, so with the idea of computing a fixed point of the pruning function is we're going to keep on pruning out single choices from any row, column or box until that isn't possible anymore. And then we'll call collapse, and then we'll call filter valid. And what we found last day is that this simple solve3 function can solve easy grids immediately. In fact, you could actually characterize easy grids as ones that can be solved using this particular function. But unfortunately, not every Sudoku grid, which you find in the newspapers, is easy. There's a whole hierarchy of difficulties. You have gentle grids, you have difficult grids, diabolical, all sorts of other ones as well. And in fact, when you try it with the gentle grid, out of the collapse function now comes about 10 to the power 29 possibilities that you need to consider. So this function will work fine for solving easy Sudoku grids, but unfortunately it's not sufficient to solve anything more complicated. So we need to think a bit more deeply. So the question now is, how can we solve any Sudoku puzzle that we can find in the newspaper, or in fact any Sudoku puzzle? And what we're going to see today is that the key is something called blocked matrices. So that's what we're going to be looking at now. It's the idea of a blocked matrix of choices. And we're going to come at this by introducing two simple concepts first. The idea of a choice matrix being void, and then the idea of a choice matrix being safe. And these are very simple concepts. So the first concept I want to introduce is that a matrix of choices is going to be called void if at least one cell has no choices. So an example of this would be if we had the top left-hand corner of our choice matrix, maybe we had a 1 here, no choices in the second square, and then a 2 and a 3 as the choice here. This would be void because there is no choice left in this square. Okay, and of course, if you ever ended up with a void choice matrix where you have at least one cell which has no choices left, that's never going to have a chance to lead to a solution, and that will be important to us in a bit. So that's the idea of what a void choice matrix is. How can we actually define what this means? Well, this is very simple. We can take a matrix of choices and we can return true or false depending on whether any of the cells in the grid are empty, so there's no choices left. This is a very easy function to define. We take our choice matrix M and we use the any predicate, or the any higher order function rather. And what any does is you give it a property like being an empty list, which is null in Haskell. Null decides if a list is empty, and any will take a predicate or a property and it will decide, does any element of a list have that property? So we're using any twice here, and what we're really saying, is it the case that any row has any empty cell? So this will return true if it finds any empty cell of choices in a matrix of choices. So that's the idea of a void matrix. The next thing I want to introduce towards defining what a blocked matrix is the idea of a matrix being safe. And we're going to call a matrix safe if all the rows, all the columns, and all the boxes are what's called consistent. And consistent is going to mean that they don't contain any duplicated single choices. So for example, if I had a top left-hand corner like this, and I had a 1 here, and a 2 and a 3 here, and a 1 here, and a 4 here, this would be an inconsistent matrix because I have a 1 here, and I have a 1 here as well. And if I ended up with 2 1s in the first row, that's never going to lead to a solution, because one of the basic rules of the game, or the basic rule of the game, is you have to have each of the numbers 1 to 9 in each row, column and box exactly once. Okay, so this is the idea of safety. A matrix is going to be called safe if every row, column and box is consistent in the sense that it doesn't have duplicate single entries. So let's define what it means for a matrix to be safe. So a matrix of choices is going to be safe. So that's going to return true or false. And this is a very easy function to define because I'm going to use a helper function. I'm just going to say if all the rows are consistent, so no duplicate single entries, and all of the columns are consistent, so all of the columns are consistent, and finally all of the boxes are consistent. So I'm just using my helper functions, rows, columns, and boxes. And of course, I haven't yet defined what it means to be consistent. So how does consistent work? Well, consistent just takes a row of choices. It's going to take a row of choices, and it's going to give back true or false. And all it's going to do is check, is there a duplicate single entry in any of these choices? So I can give you a little concrete example. So if I say consistent, start up GHC, and say, suppose we've got 1, 2, 3, 4 in the first box, and then we've got a 1, that's a single entry, and then we've got a 3 and a 4, and then we've got a 3. So that would be consistent because there's no duplicate single entries. So we do have 2 single entries here. We have a 1 and a 3, but these are different. So this is consistent. An example of something which is not consistent is if I take the same example and I just modify it a little bit. 2, 3, 4. So I have the 1 and I have the 3 and the 4. And suppose I had a 1 here. So now we have a duplicated entry. We have a duplicate single entry. This choices would never lead to a possible solution because we have 2 1s in the first row. So that's never going to give a solution because it violates the basic rule of the game. So we'll say that's not consistent. Oops. We'll say that's not consistent, and we get back the value false. Okay, so I'll leave it as an exercise for you to define this function. As I mentioned at the start of the course, I'm going to define lots of the functions that we use in the course, but from time to time I'll set little exercise to you, and if you want to do particularly well on the course, try and do these little exercises for yourself. So we've now got all the components that we need to define what it means for a matrix of choices to be blocked. So we take a matrix of choices and we give back true or false. And the idea is very simple. We combine the use of the void function and the safe function. So a matrix of choices is going to be blocked if either it's void or, so the double bar here is the Haskell OR operator, or it's not safe. Okay, so what does this actually mean? So this part here means there are empty cells. So there's choices where there's actually no choices left. And what this part here means is there could be, or there are, duplicated single cells. Okay, so this is what it means for a choice matrix to be blocked. Either there's some cells which are empty, or there's some cells where you have a duplicated single choice in a row, column, or a box. And the key idea is that blocked matrices can never give you a solution. Because if you've got an empty choice, then you can never get a solution. If you've got a duplicate, say you've got a 1, 2 places in the first row, you can never get a solution from that point onwards. And you can ask yourself, why are blocked matrices really bad for our current Sudoku solver? That's solve 3, which we talked about a minute ago. And the problem is that a choice that leads to a blocked matrix will be duplicated many times by collapse because it considers all possible combinations. So if we go back to our final solver here, when we apply the collapse function, if we have reached the point where we have a blocked matrix, then in the collapse function, that's going to be duplicated many, many times because the collapse function will consider all possible combinations of choices. So thinking about these blocked matrices is actually going to be the key to coming up with a very efficient Sudoku solver. So the idea here is we're going to actually expand choices out one cell at a time. And what we're going to do is filter out resulting matrices that are blocked before expanding further cells. And that means if we find the choice matrix which is blocked, we just abandon it completely rather than passing it into a collapse function or the collapse function, which is then going to expand that and consider zillions of possibilities which never have the possibility to succeed. So here is our final Sudoku solver. I'm going to call it solve4. And it's going to be defined as a function composition. So what we're going to do is we're going to call a function called search after a function called prune after applying choices. Okay, so let's understand what's going on here. So the first part here, prune after choices, is pretty much the same as what we had before. Choices simply takes the initial Sudoku grid and replaces each blank square by all possible choices between 1 and 9. Then we apply the pruning function once, and then we're going to pass the result of that into a function called search, which is now what we're going to write. And you might be thinking, well, why didn't I write fixed prune here? But actually, we don't need to do that. It actually turns out to be more efficient if we don't iterate the pruning function. And I'll come back to that point in a bit. Okay, so let me write then the search function, which is going to do all the work for us. So what search is going to do is it's going to take a matrix of choices and it's going to give me back all possible Sudoku grids which solve that puzzle from that point. Okay, and again, if you just want one, you simply take the head of that list. So we're going to define it by case analysis. So we pass in a choice matrix M, and then we're going to have three possibilities. So I'll use a simple guard here. The first one is if the choice matrix is blocked, that means it's never going to lead to a solution. So we may as well just stop at that point. Okay, and this is the problem, or one of the key problems with our previous Sudoku solvers. They didn't do anything in particular about blocked choice matrices, and if one of those hits the collapse function, it will consider all possible combinations of a choice matrix, which is never going to succeed. So what we're doing here is we're chopping off matrices which never have a chance to succeed by checking are they blocked, and if so, we're simply going to return the empty list because there's no possibilities for a solution. Maybe we've also reached the point, or we have reached the point, where we have a solution. So if every cell only has a single choice left, and I can define single down here, what single does is it takes a list of things and it gives you back true if there's only one thing in the list. So I could say, if you have a list with one thing, and I'm here using the Haskell wildcard pattern down here, which is the underscore. If you have a list with one thing, I could return true. And if I have any other list, I return false. Okay, so this is the simple single property. Okay, so let me get rid of that. So what this is going to do is, if we've reached the point where every entry in the grid only has a single choice, it turns out we will have actually solved the puzzle at that point, and all we'll simply do is we will call collapse. Okay, so if there's only one choice for each cell, the puzzle is done, and we just call collapse, and that will simplify it for us, and we're done. Otherwise, we need to do a bit of work. So what we're going to do is we're going to use a little list comprehension here, and let me write it down, and then I'll explain what's going on. So we're going to expand, and then we're going to have another generator here. So here's the code for the other case. So what's actually happening here? Well, first of all, what we're going to do is we're going to expand our choice matrix. And expand is a function which is going to behave in a similar way to collapse, except it's only going to expand the first cell which has more than one choice. So collapse considers all possible choices for every single cell in the grid, and that leads to a kind of combinatorial explosion for many non-trivial examples. What expand does is it only expands the first cell which has more than one choice. And again, you could look at the definition for this in the notes, which are freely available on the web page. But actually, I think it's a very nice exercise again. Try and define the expand function. So what we're doing then is we're expanding, and that will give us a bunch of matrices, potentially up to 9, if there's 9 possibilities left for the first square, which doesn't have a single choice. Then what we're going to do is for each of those matrices, we're going to prune it to eliminate any silly choices which were still left, and then we're going to pass that back into the search function again. And then what we're going to do is collect all those grids. Okay, so this is a nice kind of 3-line function definition which implements the idea of searching. And this is basically our final Sudoku solver now. This one here is a 1-line program. Well, actually not really a 1-line program because we've defined 3 other functions, search, prune, and choices. And this can actually solve any newspaper puzzle in an instant. A couple of points to note here. We don't any longer need to check for valid grids. You notice there's no filtering valid at the end here, and that's because of the way the grids are actually constructed. If you think about it and you kind of work through an example, maybe a small example, you'll find the grids which come out of this searching process are always guaranteed to be valid because of the way they're constructed. The second point I'd make is, again, I mentioned about pruning. We don't actually need to fix prune here or down here. If you fix prune here in both of these points, it's a completely valid thing to do, but it actually turns out to make the program a little bit slower, at least last time I checked. But that's the kind of thing you might want to run some experiments with. If you iterate the pruning process, I think it makes it slower, but you can try that for yourselves as well. So what we're going to do now is I'm going to move to using GHC and give you a little bit of a demo of how this solver actually works in practice. Okay, so I have a terminal window here now, and what I can do is start up the interactive version of the Glasgow Haskell compiler, GHCI, and I can input my Sudoku solver to it, and that all loads up fine, which is great. And we can have a look at the code, and you can see all the familiar stuff which we've been working with in here. Here are the basic data types. If we scroll down a bit, you'll find a number of example grids. So here is the easy grid, for example. If we scroll down a bit more, here is a gentle grid, which is a bit harder to solve. Here's a diabolical grid, which is harder still. This is an interesting one here. This is one which potentially requires backtracking to solve. So you may need to revisit your steps rather than just applying the basic rules of the game. And we'll see if our Sudoku solver can work with this one. The final 2 ones up here are particularly interesting. Here is a minimal sized grid. So this grid is mostly blanks. It's only got 17 values filled in, but it still does have a unique solution. And at the time when I was doing this, this size of grid, 17 values, was the smallest grid which was known to have a unique solution. So this is a particularly challenging problem for a Sudoku solver. And we can also, for fun, just try running a blank grid to our solver and see how it works out. So let's try some examples. So we could try the easy grid, that's no problem. We could try the gentle grid, no problem as well. Let's try the diabolical one. Yep, works fine. Let's try the unsolvable one. Unsolvable. That one works fine. That's instant as well. It's no problem for our solver. Let's try the minimal one. Oh, it doesn't terminate quite as fast, but if we wait about 5-6 seconds, then it will give us our solution. We'll come back in a minute to see how we can make this actually even faster. And for fun, let's try the blank grid as well. And of course, this is just going to spew stuff up the screen because the blank grid's got no constraints on it at all. So you can fill in numbers all over the place and get a very, very large number of solutions. But if we just wanted the first one, we can say head of solve for of blank, and we get the first one. And if we wanted 10 solutions, we could exploit lazy evaluation and just say we want take 10 of solve for blank, and we get the first 10 solutions, which is nice. So now let's return to the fact that when we did solve for of minimal, it didn't terminate as fast as the other ones. It took about 5 or 6 seconds, even on quite a fast machine here. So let's think about how we could make this even faster. And actually, we can make it faster just by using the Haskell compiler rather than the Haskell interpreter. So what I've done at the end here is I've included a simple main, just like you have in most programming languages, and it's a purely interactive program. And what it's going to do is first call the solver with the minimal grid, and then there's only one solution, so we'll take the head of the resulting list, we'll convert that into a string, and then we'll print that string on the screen. So now we can think about compiling this. So I'll leave GHCI. And now I will type GHC, which is the compiler. I will type -O2, which turns the optimizer on full. And I will type sudoku.lhs, and that will compile it for me. And now I have an executable file. And if I run that, so /sudoku, then it will terminate much more quickly now. So this is now terminating in about half a second rather than 5 or 6 seconds. So it's about kind of 10 times faster. So what we've got here in the end is a highly efficient Sudoku solver which can solve essentially any Sudoku puzzle in more or less an instant. So again, if you want to have a look at the code for this and have a play around with it, which I suggest that you do, all the code is freely available on the web page for the module, and I've also put some PowerPoint slides there which you might like to have a look at as well. So that's it for today. See you again next time.